Okay, I think we are good to go. Uh, Welcome everyone. This is the video where we're going to see three examples that we skipped in class. The first of which is from 8.2. We're looking at example 8.2.5. It's a very common type of example associated with chapter 8 and confidence intervals. And it has to do with determining a sample size. We already know that when we choose a confidence level for an interval, that level is attached to the interval width. If I want to achieve greater confidence, I can do so, but it requires widening my interval. And there's a point at which the interval might be so wide that maybe it's not a very useful estimate. So what do we do if we want to achieve a high level of confidence, but maintain an interval size that's relatively small and impressive? Well, the answer, which is the answer for many things in stats, is to change the sample size, okay? If we increase a sample size, we can actually preserve a smaller width of interval while also maintaining a high confidence level. So these questions here have us determining a sample size. Let's suppose we want to maintain a 95% level, but we want to keep our margin of error no bigger than 0.1. We want to cap the width on our interval. We need to make some decisions prior to sampling, okay? And it starts with an analysis of the margin of error portion of our formula. This problem's from 8.2. It's a proportion problem. So this expression right here is the margin of error for the proportion problems. I see Z. I see a sample standard deviation for proportions. Okay. We want this margin of error to be less than or equal to 0.1. I'm going to write that down right away. That's our goal here. Okay. Now we're going to solve this inequality. We're going to solve it for n. We're going to decide what would n have to be to keep this nice small margin of error with a 95% level. But before we solve for n, we have to plug in some other constants here, or quantities here. Let's start with the z-score. We already know that the z-score is directly attached to the confidence level itself. What is the z-score for a 95% interval? You're probably going to use inverse normal to figure that out. Go ahead and try it now if you like. Make sure that you get a 1.96. If you're using a calculator, the area below, the area value that we feed the calculator should have been 0.025, because we're taking 1 minus 0.95 and we're cutting that portion in half. So I get a 1.96 for Z. Here's the tricky part. I'm supposed to plug in for P a population proportion, but I don't know what that is. In fact, that's the value that I want to estimate. And this analysis, these sample size determinations, they're happening prior to my study. I haven't even collected a sample yet. So I don't even usually have a p-hat to plug in as an estimate. If that's the case, then you should use 0.5 as your plug-in for p. 0.5 is considered the most conservative possible estimate, because 0.5 is the p-value that you would plug in that maximizes this expression. I'm not going to get into the details of that. If you've taken a calculus class and done optimization problems, there's calculus word problems you could set up to prove that it's a 0.5 for p that maximizes this expression. In this class, you don't have to know the calculus. You just need to memorize that for lack of anything better to plug in, we want to plug in p equals 0.5. So that's what we do. And now you have this inequality, and we're going to solve. We're going to try and get n by itself. I didn't show all the steps in my work here, but it's just algebra at this point. I'll talk through some of the steps. The first thing you would do on the left side is you would divide the 1.96 over to the other side. And that would leave you with the radical by itself. At which point you square both sides. So I'm able to remove the radical from the left. I square whatever I have on the right side. And then I might multiply the n over to the right. And then the right side will be some constant times n. Let's divide both sides by that constant. So we do some division back over to the left. Try it on your own. Make sure that you get to the same result I got. N greater than or equal to approximately 96.04. But we need to pick a sample size that gives us at least, let me rephrase. We need to pick a sample size that gives us a margin of error of no more than 0.1. So even though this result is close to 96, 96 isn't good enough. Our sample size needs to be bigger than 96.04. So the rule with this type of problem is you always round up. Pick the next closest whole number that's higher than our cutoff here. My final answer, sample of at least 97 students. And you could do even more than that. If you're going to do 97, maybe make it a nice even 100. Any number bigger than 97 only increases the precision of your interval. The higher that this number goes, the smaller and smaller your interval gets, which is better. Okay. We'll do a couple more of these. Part B. Okay. We have a friend who took the class last year that had the same assignment as what was mentioned above. What percentage of students want to get a tattoo? Wait until you're at least 27 before you get a tattoo. That's my advice. Okay. Maybe I'm speaking from experience. I don't know. Anyway, we've got this friend from last year that already did this study. They have previous data that indicated 27%. That's a p-hat. It's not necessarily the right answer. But if we have prior data that suggests what p might be close to, we're going to use that instead of our conservative estimate. So the only difference between part A and part B is we have some extra info to go off of. I can use 0.27. The 1 minus p-hat becomes 0.73. Go through the same algebra again. You get n now greater than or equal to 75.7. We round up to 7.6. So what we see here is if we have some extra information that allows us to be less conservative in our choice for p, we can actually get away with even a smaller sample size than the first attempt. And that might be beneficial because that means it's less work for the researcher. For large studies, it might be more cost effective to use the smallest possible sample size you can get away with. Okay. If I didn't have this 27% to go off of, I'd be locked into the 0.5. Part C. For extra credit, we can boost our level up to 99%. Okay. This is actually going to be more work for us because, as you're going to see, it's going to require a larger sample size if I'm still trying to maintain a margin of error no bigger than 0.1. Okay. I'm also still going to use my friend's result from last year to help determine my sample size. So the only change here comes in the z-score. The z-score is what's tied to your confidence level. So we go back to inverse normal once again. I need to feed the calculator a 0.005. to get this result here. And then you work through the same algebra as before. Make sure you're trying the algebra. Make sure you get to the same place that I did. And now we need a sample of at least 131. And that's why it would maybe be an extra credit, because you have to get a bigger sample size. It's more time consuming. Okay. And that concludes example 825. I'm going to skip ahead now to the second of 3 examples in this video. We're into 8.3. And we are actually going to continue with sample size calculations. The obvious difference now is that we're dealing with mean problems. So the standard deviation that gets used is a different formula. There's no more P involved. Okay. With this example, we want a margin of error no more than 0.0001. We're going to use a 98% level. Okay. You might also be noticing that I'm using Z here, which contradicts something that was said in class. We spent a lot of time in class saying that for mean problems, you have to switch to T. Well, this type of problem is the one exception to that. We actually have to continue to use Z, and I'll tell you why. As you recall with T distributions, using them requires us to know a degrees of freedom, and using a degrees of freedom requires us to already know a sample size. Degrees of freedom is n-1. But this exercise is where we try to figure out a sample size. So it's impossible to do this and use T. You get stuck. So if this were to show up on a test, AP problem, wherever, and we're dealing with means, we have to suspend our disbelief and just go with Z. That's why the prompt says we magically know a population standard deviation. That's not very realistic, but it's something we would need to have to do these problems. Okay, so here's the margin of error. Okay, my Z value, once again, I'm using inverse normal. 98% level means you should be feeding the calculator a 0.01 area. Population standard deviation is given in the prompt. Square root of n, we need to solve for n. Test yourself on the algebra here. We're setting this margin of error less than or equal to 0.0001. You're going to divide 2.326 over. Maybe you're going to multiply the radical n over. Divide the constant on the left side, or excuse me, on the right side back over to the left. And then for a final step, you're going to square both sides. This is where you should end up. Conclusion, we round up to at least 22. Okay. I am predicting your test might have some questions about how do we modify the margin of error to get either a wider or a less wide interval. So I want you to pay very close attention to all 3 components of this margin of error formula. As sample size gets bigger, sample size lives in the denominator, so as sample size gets bigger, margin of error gets smaller, which means you can reduce the width of your interval by increasing sample size. That's going to be on your test. Changing Z. If I have a bigger Z, that would be a bigger interval. If I have a smaller Z, that would lead to a smaller interval. Z is related to your level. So higher confidence levels lead to wider intervals. Lower levels lead to less wide, skinnier intervals, but you've got those trade-offs you're dealing with. And then finally, standard deviation lives in the numerator, so a bigger standard deviation means you have a bigger interval. It's a little bit unrealistic that you could just change a population standard deviation, but if you were able to do that, yeah, making this number bigger would give you a wider interval. Keep that all in mind for your test. We're gonna zoom back out. Part B tells us the example above was possible because we knew the population deviation, which is actually unrealistic. Why would it be impossible to answer this question using t? We already talked about that. So just jot it down for your notes. To find a critical t value, we would have needed degrees of freedom, which means we would have already had to know a sample size, which would render this exercise a little bit ridiculous. So that's the answer. And we're done with the second of 3 problems. On to the last one. This is also going to be the shortest one, so we're almost done. I am skipping ahead to 8.3.6. And this example is here just to help us think about if it's safe to use T procedures. T is robust. You can sometimes get away with it even if you don't quite meet conditions. But that doesn't mean you can always get away with it. Let's look at these cases here. Scenario A, we want to estimate a GPA, average GPA. We randomly select 50 students. Here's a graph of their GPAs. This prompt does not tell us that the original population is normal, but it doesn't matter. In fact, I don't even need to look at this graph because sample size is big enough. It's safe to use T here simply because N equals 50 is bigger than 30. And we're done. Scenario B, dot plot amount of time to order a coffee, very small sample size. Okay. We don't have information about the original population distribution. We can't claim normality there. And unfortunately, this graph shows a suspected outlier. So this is a situation where it would not be safe to use T. I don't know anything about normality. I don't have a big enough sample size. Preliminary look at a graph suggests some extreme skew. Let's avoid using T. You can't really use a procedure here that we know. Scenario C, box plot of math scores for a random sample of students at our high school. I don't see any information about the original population being normal. I don't have a big enough sample size, and yet we can still proceed here because this graph, this box plot, doesn't show any extreme non-normality. It's not perfectly symmetric, but we wouldn't expect perfect symmetry. For the most part, the right half is a similar length to the left half. Unless I see extreme skew or an outlier, it is safe to use T, the robust procedure. Now, I don't want to go so far as to claim normality of anything. This doesn't prove normality. It isn't exactly symmetric. So I'm going to say safe to use T because there's no evidence of non-normality, no strong evidence. So I'm kind of non-committal here, and you should be too. But it's safe to use T. That concludes the video. Please feel free to reach out if you have any questions. You could also ask me in class. Make sure you filled out the notes for these examples so that you can make a submission on Monday. All right, thanks for watching.